So CNNs are subject, really neural networks in general, are subject to some vulnerabilities. These vulnerabilities look kind of like this. So let's say you have this image, and this is classified as a panda with, I don't know, 70% probability. And now what we do is we're bad guys. Okay, so we're going to try and fool the neural network. So we're going to take this panda and we're going to add in some noise. Okay. To the human, this looks like just random noise. But unfortunately, to the neural network, this is going to be enough of a change. Then when I say add, right, we're taking every pixel, pixel, and so on, and just adding. So we're making small tweaks to every pixel of the panda. And what we're going to end up with is something that to our eye looks identical, right? Because we can't perceive a difference between this panda and this panda because we've just made small tweaks to particular images. The problem is we have totally fooled the neural network because the neural network now classifies this as a gibbon. And this is with an extremely high probability, right? 98% convinced that this is a gibbon. Wow, that's a problem, right? And so clearly the neural net is not actually responding to exactly the same thing that humans are responding to, right? It can get fooled by these small differences. First, let's look at where exactly did this error, this random noise come from. Well, basically, what happened is an adversary like us trained this. We basically take this input, feed this into whatever neural network or pre-trained neural network. So let's say a VGG19. The last layer of this is a softmax. And what we do is we look at the gibbon output. Let's call this epsilon, okay, because it's small changes. Compute the partial derivative of the gibbon with respect to this epsilon picture here, right? So we're taking the panda plus epsilon, feeding this in, and then we're computing the partial derivative of the gibbon with respect to epsilon. So what that really says is what sort of a change in gibbonness will happen if I increase a pixel here, and a pixel here, and a pixel here, and so on. So we'll go ahead and do this computation and then do gradient ascent. Gradient ascent because we want to be increasing the gibbonness. And we'll do this. Only thing we'll have to have is a little bit of constraint to just ensure that our epsilon never gets too big. So we might ensure, for example, that if our initial values are between 0.0 and 1.0 for our pixel values, that our epsilon values, no individual epsilon value is bigger than 0.01, right? So we can't see, I don't think we'll be able to perceive a 1% difference in RGBness and so we'll have some value here. That'll basically ensure that this is sub-perceptual. So that'll be our constraint as we're doing our update in our gradient ascent. Sub-perceptual for humans, not for neural networks, unfortunately. And so that would then allow us to come up with this image. For this particular neural network, pre-trained with these particular weights, then we've got a way to fool it. This is what's called an adversarial example. You might say, well, okay, how this was created was by actually having the neural network in the weights. If we just make sure to have our weights be hidden so that the adversaries can't get hold of it, then we'd be safe, right? And the answer is unfortunately no. That adversaries actually, even if this is a black box, as long as they have the ability to feed in images and find out what the results are, that they can do this as well. So as you can imagine, what you can do is just take this panda image and say, okay, we'll feed in the panda image by itself. What are my values I get back? And what's the gibbonness, right? I get my value back. So I get all these values. And then I go through and I say, okay, if I increase a pixel here, what happens to the gibbonness? Does it increase or does it decrease? Okay, so I can then go ahead and adjust one pixel, and then I can do it in just another pixel, and so on. So that's one way you can do it. It turns out even if you don't have the actual values coming in here and just have the classification, it's possible to do this as well. It turns out that you can have vulnerabilities not just with computer images, but also out in the wild. Let me give you an example. This was a paper that was done where they created some stop signs. So this is an example where they actually created a printout of something to paste over a stop sign. So you look at this stop sign and it looks just like a stop sign. I mean, it's a little light here for some reason, but you wouldn't, as a human, think anything but that that's a stop sign. Okay. This actually gets recognized, and this was by a CNN classification that was classified to recognize road sign. This was actually recognized as 45 mile per hour. Well, as you can imagine, the difference between stop and 45 miles per hour is pretty extreme, right? If you've got your self-driving car that comes up to an intersection, if it sees a stop sign, presumably it's going to stop, and if it sees a 45 mile per hour, it might just step on the gas. That would be very bad. This required replacing the whole image, because basically what we have in here is little bits of epsilon, just like we had in our previous example. This is an example where they took an existing stop sign and then just figured out how they could paste on various pieces to it. So it's a little more noticeable because they have much less area to work with. So they're pasting on these things to it. This also got categorized as a 45 mile per hour. Again, as a human, you'd look and you'd say, well, someone's put some stickers up on that, but it sure is still a stop sign. Okay? And this is yet another example. Here, they put up stickers that actually, so as a human, you look and say, hey, someone's defaced that stop sign. They put a love and hate thing on the stop sign. Well, no, actually, that wasn't what they were trying to do. They weren't trying to say anything about love and hate. They were trying to say, I'm trying to convince your neural network that this says 45 miles per hour. So these vulnerabilities to image recognition can actually extend out into real life. One can, again, completely replace an image, or also one can go ahead and put these in. Now, this can be used for good as well. You can imagine facial recognition out there, where you could have small little, let's say, well, tattoos is probably going a little far, but small makeup things you might wear on your face such that you couldn't be recognized. I don't know whether you've seen also people just with ball caps with a little infrared LED on, and that just bathes your face in such a way that most facial sensors just see your face as this just bright blob. So again, facial recognition won't work. So it's not clear that all adversarial relationships with neural networks are bad. Perhaps sometimes they're good, but just be aware that these are vulnerabilities. And really what they point out is that neural networks do not work like you and I work, right? We all work, we have some shared physiology with regard to shared RGB. We have our brains work in similar ways, and neural networks just do not work that way, and they're attending to some things that we do not attend to.